September 15th, 1943. The waters off Salerno, Italy. A German E-boat races through the darkness at 40 knots, its engines screaming as it prepares to unleash torpedoes against Allied landing craft ferrying soldiers to the beachhead. The commander peers through his binoculars, calculating range and angle. Then, without warning, the sea itself seems to erupt. The E-boat's hull buckles inward as if struck by an invisible fist. Metal screams. Water floods the engine room. Within 90 seconds, the vessel is gone, dragged beneath the Mediterranean. No shell was fired, no torpedo streaked through the water. The crew never saw their attacker. They were killed by sound. This is the story of the acoustic mine, perhaps the most psychologically devastating naval weapon of the Second World War. Whilst conventional mines waited passively for contact, these devices hunted their prey, listening in the darkness for the specific acoustic signature of an enemy vessel. They represented a revolution in naval warfare, turning the sea itself into an intelligent, patient killer. For the Kriegsmarine, they became a nightmare that could not be fought, could not be seen, and could not be escaped. A weapon that transformed every voyage into a game of murderous chance. The problem facing the Royal Navy in 1939 was brutally simple. Germany possessed one of the most formidable surface fleets ever assembled, and British mines were embarrassingly ineffective against it. Traditional contact mines, tethered beneath the surface, required a vessel to physically strike them. German minesweepers had become extraordinarily proficient at clearing these devices. Magnetic mines, introduced early in the war, detected the steel hulls of ships passing overhead and detonated automatically. They achieved devastating success initially, sinking over 60 British vessels in the first months of deployment. But the Germans quickly developed degaussing equipment, wrapping ships in electromagnetic coils that neutralized their magnetic signatures. By mid-1940, magnetic mines had lost their edge. The statistics told a grim story. British mine layers were sowing thousands upon thousands of mines in German shipping lanes, yet the Kriegsmarine continued operating with relative impunity. Estimates suggested that fewer than 1 in every 100 mines deployed actually destroyed a target. The mathematics were staggering. At current rates, Britain would need to manufacture and deploy approximately 500,000 mines to meaningfully disrupt German naval operations. The industrial capacity simply did not exist. Meanwhile, German U-boats prowled the Atlantic with increasing boldness. E-boats attacked coastal convoys, and surface raiders threatened vital supply lines. The Royal Navy needed a mine that could not be swept, could not be neutralized, and could discriminate between Allied and enemy vessels. They needed something that seemed, in 1940, utterly impossible to create. The solution emerged from the Admiralty mining establishment at Havant, Hampshire, where a team of engineers and physicists had been exploring an entirely different approach to naval mines. Rather than detecting a ship's presence through physical contact or magnetic field, they would detect it through sound. Every vessel, they reasoned, produced a unique acoustic signature, a combination of engine noise, propeller cavitation, and hull vibration that traveled through water far more efficiently than through air. If a mine could be designed to recognize these specific sounds, it could lie dormant whilst Allied ships passed overhead, then activate only when enemy vessels approached. The technical challenges were extraordinary. The mine needed hydrophones sensitive enough to detect a ship at useful range, but not so sensitive that they triggered on waves, marine life, or distant thunder. It required electronic circuits capable of distinguishing between the low-frequency throb of a cargo vessel and the high-pitched whine of a military engine. Most critically, it needed a power source that could remain operational for months, submerged in seawater, maintaining constant vigilance in the darkness and pressure of the ocean floor. The battery technology of 1940 could barely power a torch reliably for a fortnight. The device they eventually produced, designated the Mark 14 acoustic mine, was a masterpiece of miniaturized electronics. The mine itself resembled a large oil drum, roughly 1 meter in diameter and weighing approximately 700 kilograms. Inside this steel shell sat the most sophisticated signal processing equipment Britain had ever miniaturized. 4 hydrophones, positioned at right angles around the mine's circumference, listened continuously to the underwater soundscape. These acoustic sensors were themselves engineering marvels, each containing a piezoelectric crystal that converted minute pressure variations in water into electrical voltage. The crystals had to be precisely calibrated, as variations of even a few micrometers in thickness would alter their frequency response enough to render the mine ineffective. These acoustic sensors fed into an amplification circuit that boosted the faint vibrations of distant propellers into measurable electrical signals. The challenge here was extraordinary. A ship's propeller at 500 meters distance produces acoustic pressure variations of approximately 0.0001 pascals, roughly equivalent to the sound of a butterfly landing on a leaf in air. Yet the amplification system needed to boost this whisper-quiet signal without also amplifying the ambient noise of the ocean, which included everything from shrimp clicking their claws to distant tectonic shifts. The engineers at Havant solved this through a cascade of 3 amplification stages, each increasing signal strength by approximately 40 decibels, while simultaneously filtering out frequencies outside the operational range. The amplified sound then passed through a series of tuned filters, each calibrated to respond to specific frequency ranges that corresponded to enemy warship engines, which typically operated between 300 and 800 revolutions per minute, producing distinctive harmonic signatures. German destroyers, for instance, typically used MAN diesel engines running at 450 revolutions per minute, creating a fundamental frequency of 7.5 Hz with harmonics at 15, 22.5, and 30 Hz. E-boats employed Daimler-Benz petrol engines at higher speeds, producing a characteristic 12 to 15 Hz signature. British vessels, by contrast, predominantly used steam turbines that produced a fundamentally different acoustic spectrum. The filters were constructed from precision-wound inductor coils and capacitors, each component selected to tolerances of less than 1%. A single, mismatched component could render the entire mine blind to its intended targets. The true innovation lay in the discrimination circuit. Rather than simply detonating when any loud noise occurred, the Mark 14 analyzed the pattern of sound over time. It listened for sustained, rhythmic noise consistent with a ship's approach, ignoring transient sounds like explosions, wave crashes, or even the sonar pings of Allied vessels searching for conventional mines. The mine essentially counted propeller revolutions, waiting until the acoustic signature indicated the target was directly overhead before triggering its 300-kilogram charge of Minol explosive. The detonation was delayed by precisely 1.2 seconds after the sound reached peak intensity, calculated to position the blast beneath the vessel's engine room or magazine, maximizing destructive effect. Power came from a revolutionary high-capacity battery system developed specifically for the weapon. Using zinc-silver oxide chemistry, these batteries could operate continuously for up to 90 days whilst submerged. An extraordinary achievement, given that contemporary submarine batteries required recharging every few days. The entire electronic system drew less than 2 watts of power, roughly equivalent to a modern LED bulb, yet it processed acoustic data with remarkable sophistication for 1940s technology. Manufacturing took place at several locations, with final assembly conducted at the Royal Navy's facility in Portsmouth. Production was deliberately slow and expensive. Each mine required approximately 200 hours of skilled labor to construct, and the hydrophones alone cost more than 15 conventional contact mines. The Admiralty authorized production of approximately 50,000 units between 1942 and 1945, though exact figures remain partially classified. This seems a modest number until one considers that each acoustic mine had roughly 50 times the probability of a kill compared to conventional weapons. In pure mathematical terms, 50,000 acoustic mines represented the destructive potential of 2.5 million contact mines. The first operational deployment occurred in June 1943, when RAF Bomber Command seeded the approaches to Hamburg harbor with 200 Mark 14 mines. German Naval Command had no idea what was happening. Ships that had safely traversed the channel for years suddenly began exploding in waters that minesweepers had declared clear. A destroyer, the Z-27, broke in half and sank within minutes, taking 280 crew with it. Survivors reported that the explosion came from directly beneath the vessel's engineering spaces, with no visible torpedo track or surface detonation. 2 days later, the supply vessel Lübeck detonated an acoustic mine and went down with its entire cargo of ammunition and fuel. The blast was so powerful that windows shattered in houses 3 kilometers inland. Over the following fortnight, 7 more vessels were lost. Each explosion followed an identical pattern: catastrophic hull failure, amidships, rapid flooding, minimal survival time. Panic spread through the Kriegsmarine like infection through a wound. Minesweepers swept the channels repeatedly, cutting the mooring cables of contact mines and triggering magnetic mines with electromagnetic pulses. But the acoustic mines, sitting silent on the sea floor, ignored these countermeasures entirely. They were waiting for the sound of engines. German mine warfare experts examined fragments recovered from sunken vessels, searching desperately for clues about the new weapon. What they found puzzled them completely. The explosive damage patterns were consistent with mines, but no mine casings were ever found, no mooring cables cut. The weapons appeared to be ground mines, yet they detonated with uncanny precision beneath the most vulnerable points of each ship. By August 1943, acoustic mines had been deployed in the Kiel Canal approaches, outside Brest, throughout the English Channel, and across the North Sea shipping lanes. The impact on German logistics became severe. Critical supply runs to Norway were cancelled entirely. Submarine transits from French bases to Atlantic patrol areas dropped by more than half. Records from the period, recently declassified, reveal the psychological impact on German crews. Sailors began to refuse assignments on vessels departing Hamburg. Officers filed reports describing crews paralyzed by unnamed dread and refusing duty on the grounds of certain death. Some commanders ordered engines shut down whilst drifting through suspected minefields, hoping to slip past undetected, but this left ships vulnerable to currents and collisions. Others ran engines at maximum power, attempting to speed through dangerous waters, but this merely made the acoustic signature clearer and more distinct. A few experimental attempts were made to disguise engine sounds by playing gramophone recordings of different vessels, but the mine's sophisticated discrimination circuits were not fooled. There was no effective response. The mines could not be fooled, could not be avoided, and could not be cleared. Every voyage became an exercise in existential terror, every departure a potential death sentence. If you are finding this interesting, a quick subscribe helps more than you know. The Germans, predictably, attempted to develop equivalent weapons, but their efforts lagged significantly behind British capabilities. German acoustic mines, designated oyster mines when they eventually appeared in late 1944, used cruder circuitry that frequently detonated on ambient noise, making them nearly as dangerous to Axis shipping as to Allied vessels. The fundamental problem was one of electronic sophistication. British radar development, particularly the cavity magnetron and subsequent refinements in microwave technology, had forced extraordinary advancement in miniaturized electronics and signal processing. Teams at the Telecommunications Research Establishment had developed techniques for building reliable vacuum tube circuits no larger than a cigarette packet. This created a technological foundation that German industry, increasingly bombed and resource-starved, simply could not match. German engineers were still using technology equivalent to civilian radio receivers from the 1930s, whilst British designers had leapt forward into what would later be recognized as the early stages of modern signal processing. The Soviet Union obtained several intact Mark 14 mines from wrecks in the Baltic and attempted reverse engineering, but Soviet electronics manufacturing lacked the precision tooling necessary to reproduce the discrimination circuits. Soviet copies, when they eventually entered service in 1946, had failure rates exceeding 40% and frequently detonated on their own submarines. By contrast, American acoustic mines, designated Mark 24, and developed with direct British technical assistance from 1943 onwards, began deployment in the Pacific Theater in 1944. American manufacturing prowess allowed rapid scaling of production. Where Britain produced approximately 50,000 acoustic mines during the entire war, American facilities manufactured more than 80,000 Mark 24 units in 18 months. These weapons proved devastatingly effective against Japanese shipping, which lacked even basic degaussing equipment and remained wholly unprepared for acoustic weaponry. Japanese records captured after the war revealed that acoustic mines accounted for approximately 25% of all Imperial Navy vessel losses between June 1944 and August 1945, despite representing fewer than 8% of all mines deployed. The psychological impact paralleled that experienced by the Kriegsmarine. Japanese captains began treating routine coastal transits as suicide missions. The comparative statistics are remarkable and bear detailed examination. A traditional contact mine had approximately a 1.2% probability of sinking a ship during its operational lifetime, which averaged about 6 months before marine growth fouled the mooring mechanism, or storms tore it loose. Magnetic mines, before countermeasures were developed, achieved roughly 8% probability of kill, though this figure dropped to less than 2% after degaussing became widespread in 1940. The Mark 14 acoustic mine, according to post-war analysis conducted by the Admiralty Mine Warfare Department, achieved approximately 47% probability of kill over its 90-day operational lifetime. Nearly half of all acoustic mines deployed successfully destroyed a target. This represents 40-fold improvement over contact mines and made the acoustic mine, pound for pound, the most efficient ship-killing weapon in the Royal Navy's arsenal. When cost is factored in, the analysis becomes even more striking. A contact mine cost approximately £15 to manufacture and deploy. An acoustic mine cost £780, roughly 52 times more expensive. Yet the acoustic mine's effectiveness was 40 times greater, meaning that in pure cost per kill terms, it was actually more economical than conventional weapons. The Admiralty estimated that acoustic mines saved Britain approximately £12 million in naval construction costs, as the weapons eliminated enemy vessels that would otherwise have required multiple destroyer or aircraft sorties to neutralize. The impact on German naval operations was profound, measurable, and ultimately strategic rather than merely tactical. Kriegsmarine sortie rates from French and Belgian ports declined by approximately 60% following the introduction of acoustic mines in those waters. E-boat attacks on Channel convoys, which had averaged 12 per week in early 1943, dropped to fewer than 3 per week by October. Supply runs to German garrisons in Norway became so hazardous that the Wehrmacht began rationing ammunition, accepting shortages rather than risking transport vessels. The psychological effect amplified the material damage in ways that confounded traditional military analysis. German naval commanders began routinely rejecting missions, citing unacceptable risk levels that, on paper, appeared manageable. Morale plummeted not just among crews, but among families in port cities, where every departure meant watching loved ones sail into what had become, effectively, a mechanical abattoir. Sailors considered assignment to any vessel operating in mined waters, essentially a death sentence. Some deserted, rather than sail. Others reported sick with psychosomatic illnesses that mystified medical staff, but had a single common cause: paralyzing fear of the listening mines. The weapon had achieved what military strategists call denial of sea control, not through superior firepower or numerical advantage, but through the simple expedient of making German naval operations psychologically and practically untenable. Interestingly, the acoustic mine influenced post-war naval technology far beyond its immediate tactical application, spawning entire branches of engineering that remain active today. The signal processing techniques developed for the Mark 14, particularly the methods for discriminating meaningful acoustic signals from background noise in real time, led directly to improvements in sonar systems deployed on submarines and destroyers throughout the Cold War. Engineers who had worked on acoustic mine development at Havant went on to design the British Type 184 sonar, which itself became the basis for NATO standard submarine detection equipment. Modern torpedoes employ descendants of the same acoustic homing technology, listening for propeller sounds and actively pursuing their targets through three-dimensional maneuvering that would have been impossible without the foundational work done on mine hydrophones. Anti-submarine warfare helicopters use dipping sonar that operates on principles remarkably similar to those pioneered in the acoustic mine's hydrophone arrays, even down to the frequency response curves and discrimination algorithms. Even contemporary naval architecture reflects lessons learned from this weapon in ways most people never recognize. Modern warship propellers are designed with acoustic stealth as a primary consideration, shaped to minimize cavitation noise and coated with sound-dampening materials, all in direct response to the threat established by Britain's listening mines. The entire field of underwater acoustics, which now encompasses everything from submarine detection to seismic exploration, owes its practical foundations to the engineering problem solved between 1940 and 1943 at a small facility in Hampshire. When oil companies use acoustic surveys to map undersea petroleum deposits, they are using descendants of the technology developed to sink German destroyers. When marine biologists study whale communications through hydrophone arrays, they are employing instruments whose direct ancestors hunted ships in the darkness of occupied European waters. Several surviving examples of the Mark 14 exist today. One is displayed at the Imperial War Museum in London, its casing cut away to reveal the intricate electronics within. Another sits in the Royal Navy Museum in Portsmouth, recovered from the Channel floor in 1968 by commercial divers. These artifacts offer a fascinating glimpse into the sophistication of wartime technology. Standing before the Portsmouth example, one can see the glass vacuum tubes, the precision-woven transformer coils, the carefully potted circuits sealed in wax to resist seawater. It represents an astonishing achievement of miniaturization for its era, cramming the electronic complexity of a small radio station into a package that could withstand depths of up to 200 meters and function reliably for months without maintenance. The legacy extends beyond technology into strategic thinking. The acoustic mine demonstrated that naval supremacy could be achieved not merely through building larger fleets or more powerful guns, but through asymmetric application of advanced technology. Britain, outgunned and outnumbered in conventional naval terms, nevertheless controlled the seas through intelligent application of scientific principles. This lesson profoundly influenced Cold War naval strategy, where nuclear submarines relied on acoustic stealth and sensor superiority rather than surface firepower. The notion that silence, patience, and intelligent discrimination could defeat brute force became a cornerstone of modern naval warfare. Return now to that E-boat commander in the Mediterranean darkness of September 1943. He has perhaps 15 seconds of life remaining, though he does not know it. Far beneath his racing vessel, a Mark 14 mine has been listening to his engines for the past 40 seconds. Electronic circuits have measured the frequency, counted the revolutions, determined that this acoustic signature matches those stored in its primitive memory. The discrimination circuit has ruled out ambient noise, eliminated the possibility of friendly vessels. Now the firing circuit activates. High voltage current flows to the detonator. The delay timer counts down its final 1.2 seconds. What makes this weapon so remarkable is not merely its effectiveness, but its elegance. It required no human operator to aim it, no gunner to sight it, no sailor to risk their life deploying it. It sat alone on the ocean floor, patient and implacable, executing its function with mechanical precision. It could not be reasoned with, could not be frightened, could not be fooled. It simply waited, listened, and killed. In the calculus of war, where every advantage compounds and every weakness cascades, the acoustic mine gave Britain something more valuable than firepower. It gave them certainty. Certainty that German vessels could not pass without loss. Certainty that no harbor was safe, no channel secure. Certainty that the sea itself had become their ally. The E-boat's hull ruptures upward, the force of the blast lifting its stern clear of the water. Metal fragments scythe through the darkness. The Mediterranean closes over the wreckage in seconds, as it has done over countless vessels before. One more victim of the weapon that never fired a shot, never needed to. It simply listened, waited, and understood exactly what it was hearing. That understanding changed naval warfare forever.